My name is Alexandra Pope, and I'm very excited to be telling you about the Origin Space Telescope. Origin Space Telescope is one of the 4 large mission concepts that's being studied by NASA in preparation for the Decadal Survey. Origins is a large, cold infrared telescope. And if you'd like to learn more about this mission and all the science we'll do, I'll refer you to the NASA booth in the corner where we have brochures and a list of other events that we have here at AAS. And in addition to the talks, we're also doing a little scavenger hunt. So for those of you participating, the secret word for this talk is feedback. So the Origin Space Telescope will be a general observer facility. It covers a wide range of science areas, from protoplanetary disks to exoplanets to the dark ages. In the talk today, I'm going to focus on how origins will be crucial for addressing the coevolution of supermassive black holes and their central galaxies. From the known relationship in the local universe, we know that the mass of the supermassive black hole in the center of galaxies correlates with the mass of the central bulge. And this implies that these 2 major components of galaxies co-evolve together over cosmic time. We heard in the last talk how crucial the infrared is for placing the supermassive black holes in the context of their galaxies. And in fact, the Origin Space Telescope will be able to simultaneously measure the star formation rates, the black hole accretion rates, and the feedback in the same galaxies over much of cosmic time. So we know that feedback is important for galaxy evolution, both from observations and simulations. So on the left here is a simulation of a galaxy forming from the FIRE group, which is feedback in realistic environments. And it's showing the gas at different temperatures. The magenta gas, which is concentrating towards the centers, is the cold molecular gas. The green is the warmer ionized gas, and the red is the hot gas. And you can see how you can see this effect of feedback and outflows in the simulations. We also see this effect in observations. So on the middle right over here, we have MED2, our favorite starbursting feedback galaxy in the local universe, which clearly shows winds being blown out of the center of what's a typical disk galaxy as seen through its stellar light distribution. The X-rays and the infrared reveal these massive outflows. And on the bottom is another example of a galaxy cluster where the central CD galaxy has an AGN that's blowing out these radio jets. So if we look again at MED2 on the left here, this is a transition from Hubble images through to the infrared Spitzer images. And so you see how we've got the disk of stars, and as we move to longer wavelength, the infrared is revealing this excited gas that's being expelled from the center of galaxy from the intense star formation that's occurring at the center. Now, in the nearby universe, infrared selection of galaxies shows some very dynamic systems. It's showing galaxies in the process of major mergers, where the merger is triggering the increased star formation and the increased dust observations. And this is seen both in observations on the left and also in simulation. So again, this is a simulation of galaxies merging, showing the distribution of stars as you would see in a Hubble image. And what's apparent in both the observations and the simulations is the dark dust lanes that appear on these images that are obscuring our view from these beautiful Hubble images. And in fact, the majority of the light that is coming out from the stars forming in these galaxies is getting obscured by the dust and re-radiated in the infrared. So the infrared is crucial to complete the picture. But this is not just happening in extreme galaxies. So even galaxies that are relatively normal have the majority of their light obscured by the dust. And so the plot on the left is showing the total star formation rate buildup in the universe as a function of cosmic time, as traced through the ultraviolet in blue and the infrared in red. And you can see that the dust-obscured star formation for the period of cosmic time that we've tracked it dominates over the unobscured star formation. On the right here, we have a relatively normal nearby galaxy, again transitioning from showing the optical light through Hubble to what we see with Spitzer. And clearly we need both pieces of the puzzle to understand the star formation happening in this galaxy. We can see from the plot on the left that above about a redshift of 3, our picture in the infrared is fairly incomplete. We do have observations of dusty galaxies in the infrared, but they tend to be more extreme systems, and we haven't had the facilities or the observations to really probe this down to the typical galaxies. In addition to that, we have a challenge in determining the redshifts to be able to place these dusty galaxies within the 3D structure of the universe. And so infrared, specifically infrared spectroscopy, can address many of these issues. And here's some examples of how ALMA is doing this. So ALMA starts around 400 microns, so it can see redshifted infrared lines. And so what we're looking at on the left is some observations of C+, which is the dominant cooling line in galaxies that does a really good job of tracing star formation. These galaxies are redshift 5.3, and so the observations of C+ have given us insights into how the ISM is fueling the star formation in these galaxies. And on the right is another observation from ALMA, superimposed on the Hubble distribution of stars, showing the hot ionized gas from the central supermassive black hole in this galaxy that's being heated, and we're seeing it in the infrared lines. So how is the Origin Space Telescope specifically going to address this problem of coevolution of supermassive black holes and galaxies? It's basically with infrared spectroscopy. This plot here shows over an order of magnitude gap in our access to key spectral diagnostics for these processes. So what I'm showing here is a galaxy spectrum tipped on its side with the observed wavelengths of some key lines, and then showing how they redshift over cosmic time. JWST is this region down here, and ALMA is this region down here. So currently there's a huge gap in our access to these diagnostics. And we have had infrared facilities before. We've had Spitzer, we've had Herschel, but we've never had the sensitivity and the wavelength coverage to really push these spectral lines beyond the local universe. So this is very untapped territory. And this would be fine if this were an empty region, but these lines are very powerful. You can see in red are lines that specifically trace the AGN, in blue lines that trace the star formation, and in yellow lines that trace the warm molecular gas. So the next slide shows some of these lines in action and how they're used for these science questions. On the top left is an OH profile from a nearby galaxy showing how we can measure the outflows and the feedback. In the middle is a region of the mid-infrared spectrum from Spitzer that shows in the same galaxy how you can use the pH lines to measure the star formation and the neon lines to measure the AGN. And on the right, just demonstrates that there are many other rich diagnostics in this region as well. So again, the infrared is very unique in that it can simultaneously measure the star formation rate, the black hole accretion rate, and the outflows in the same galaxies over cosmic time. So this just shows where Origins is in wavelength space relative to some other missions. It seems to be sort of a natural progression as we move from Hubble to Webb, out pushing to longer wavelengths. And if our mission is really to push the redshift frontier and get out to the highest redshifts, Origins also has a unique niche there. Hubble has shown us galaxies out into the epoch of reionization. The James Webb will push us back to seeing the first galaxies. The Origin Space Telescope, with access to these warm molecular hydrogen lines, can actually see the first structures collapsing before we have all the metals that we need to detect in these other facilities. So it's got unique parameter space there. And I'll finish there. I just want to remind you that we have a lot of other activities here. There's more information at the booth. Please grab a brochure and come and talk to any of the OST team members if you're interested in this mission. Thank you.